In this video, we want to find the inverse of a function f of x equals 4 minus x squared with this condition that x is less than or equal to 0. So the task is to find the inverse function and then sketch its graph. So first thing, I want to talk about this added condition that x is less than or equal to 0. If we think about the graph of f of x equals 4 minus x squared, so it's a degree 2 polynomial. It's a quadratic function. So the graph is a parabola. And the fact that you have a negative number in front of the x squared tells us that that parabola opens downward. The positive 4 here is actually a vertical shift up 4. And so the graph of f of x equals 4 minus x squared, it's going to be a parabola opening downward, but with a vertex shifted up 4. 1, 2, 3, 4. So the vertex is here. And let's see, I mean, if x is 2 or negative 2, this will be equal to 0. So it's going to touch the x-axis at 2 and negative 2. So notice that if we did not have this requirement, if we were just looking, we were told, okay, consider f of x equals 4 minus x squared. This fails the horizontal line test. This is not a one-to-one function. And so it would not have an inverse. So there's this added condition here, x is less than or equal to 0. This is referred to as a restricted domain. And it's necessary with these quadratic functions because if the graph is a parabola, it's going to fail the horizontal line test every time. But if we restrict the domain with something like x is less than or equal to 0, so the x's that are less than, here's 0, x's that are less than or equal to 0 are on the left side here. And so we get rid of all of the points on this graph with a positive x. You'd get rid of all of these points. And so now we have just half of the parabola, the half that's to the left of the y-axis there. And now notice it does pass the horizontal line test. And so now it does have an inverse. Okay, so this is the graph of our function f, which I want in blue here. Now, we could actually graph the inverse just based on the graph of f here. And in fact, I mean, maybe I'll go ahead and do that. So without even finding the equation for the inverse, if we have the graph of f on the page here, then we could sketch the graph of the inverse function. Maybe I think I'm going to hold off actually on that. Okay, let's find the equation for the inverse. So if we're starting with f of x equals 4 minus x squared, and let me tack on that condition. Let's consider that sort of part of the function for now. So we should replace f of x with y, and then we should swap x's and y's in this equation. So this becomes x equals 4 minus y squared with y less than or equal to 0. Swap x and y all the way across the statement of this function. So the requirement that x is less than or equal to 0 in the original function will translate to a requirement that y is less than or equal to 0 in the inverse function. So now we're actually, now that we've swapped x and y, we're actually dealing with the inverse function at this point. But we want to have that function written as a function of x. We want it solved for y. So now the task is to solve for y, isolate y. So I'm going to rewrite this equation down here. So if I want to isolate y, I'm going to add y squared to both sides. So I have y squared plus x equals 4. And then subtract x from both sides. So y squared equals 4 minus x. And then take the square root of both sides. Now normally when you solve by taking square roots, we would write y equals plus or minus the square root of 4 minus x. But we can't keep it as plus or minus because then this equation does not describe a function. You plug in most x values that you plug in, anything other than 4, you're going to get two different y values as your output. Plug in x equals 1. You get y equals plus or minus the square root of 3. That's not good. That can't happen with a function. So we have to choose one or the other. That's where this condition comes into play. Okay, well, if the original function was defined with x less than or equal to 0, then we need to set up the inverse function where y is always less than or equal to 0. So in this case, it's reflected from this restriction, we should choose the negative root. Now, for the record, well, let me write down this inverse function first. For the record, that can change depending on what the restriction was. You may have another problem where you have the restriction x is greater than or equal to 0. Say you kept the right half of the parabola. Well, then that would translate to y is greater than or equal to 0, so we would have taken the positive root at this point. So choosing the positive or the negative root at this stage of the problem depends on the restricted domain. And you may in some problems choose the positive root, you may in some problems choose the negative root, but it depends on your restriction here, and then what that means for your y values here. Okay, so that's the equation for the function. We found the inverse function. Now, getting back over to the graph. So if we graph this, it's a square root function, so we know the general shape of the graph is like this, but it's transformed. The negative in front of the x is going to flip it horizontally across the y-axis. The negative in front is going to flip it vertically. And then there's a horizontal shift of 4. Let's just plug in some points. Let's do that. So if we plug in, let's say x equals 4 into this equation. In fact, I'll make a little t-chart over here. So take an x value, plug it into that inverse function. I'm not going to have room. So I'm a little rushed when I'm making these videos, so they're not coming out perfect by any means. But I appreciate you guys bearing with it. Yikes. So this is negative square root of 4 minus x. I hope that's legible enough for you. So if we plug in, well, here, let's just do this. Plug in x equals 0. Then the output will be negative square root of 4 minus 0. So negative square root of 4, negative 2. So we can plot a point at 0, negative 2, right here. Let's say we plug in x equals, I don't want to plug in x equals 1. I don't want to deal with the square root of 3, or square root of 2 for that matter. What if we plug in 3? Then we'll have negative square root of 4 minus 3. Well, that's the square root of 1, so negative 1. So when x is 3, y is negative 1. That's that point right there. And last value to plug in, if we plug in x equals 4, you'll have 4 minus 4 under the radical, so 0. Negative square root of 0, that's just 0. So we have a point at 4, 0. And that's actually the end-point for that graph. It looks like this. And then there's the graph of f. So this is our square root graph reflected both horizontally and vertically. So it's flipped across the x-axis and the y-axis and shifted to the right 4 units with that 4. The thing I wanted to point out is that this is, for one thing, symmetric across the line y equals x, like the graph of a function and its inverse is supposed to be. And if we look at the coordinates of the individual points, here you've got a point at 0, 4. On the inverse, we've got a point at 4, 0. And this is where I was saying a moment ago we could go ahead and graph just based on the graph in blue there by doing this sort of thing. Here we have a point at negative 2, 0. On the inverse graph, we have a point at 0, negative 2. So you just flip the x and the y in these coordinates. One last thing I'd like to point out, looking at this graph overall, notice how, let's say we write down the domain and the range of f. Domain of f, range of f. So the domain of the graph in blue, the graph of f, is negative infinity up to 0. Lowest x to highest x included on that blue graph. Negative infinity to 0. And the range, lowest y to highest y for the graph in blue, would be negative infinity up to 4. Negative infinity to 4. Now notice, if you look at the graph in red, so the graph of the inverse, domain is negative infinity up to 4. It's equal to this. This is equal to the domain of F inverse. And the range of the graph in red would be negative infinity up to 0. It's this. This is the range of F. And again, I mean, we see that what happens is what's intended to happen with all inverse functions, which is the domain of the original function equals the range of the inverse. And the range of the original function equals the domain of the inverse. So it all plays out the way we expected it to.